Mhm.
Yes, and Inatani-san,
Yeah.
will you mind if we will interrupt you talking with questions?
Yeah, of course.
Is it possible, yeah?
Yeah. Yes, of course.
Good. Mm. One more minute. And we will start. Yeah, I think that we can start the seminar. It is a little bit unusual for us because we usually start at 12 and it is 11:30. But nevertheless, let us start our seminar. And ahai gozaimasu. Inatani-san, yeah, it is a pleasure to introduce our speaker, Inatani-san from Department of Physics and Research and Education Center for Natural Sciences of Keio University in Kanagawa. He will be the main speaker, but he will discuss in his talk the paper which was published recently in Physical Review C with 3 co-authors. I hope that all co-authors will be present here. Shigehira Yasui and Minatanita and well, I didn't find a lot of information in the internet to introduce all co-authors, but what I found out, this publication activity, it is impossible to hide in the internet, and I'm extremely impressed in this because, for instance, Inatani-san, he seems to be the youngest of the co-authors, and in 10 years he published about 60 publications in very good journals. And Shigehira Yasui, he published 3 times more papers for a longer period of time. And as far as Nito-san, he is a very famous scientist. He published so many papers, well, 400 papers. So, well, it is difficult just to look through the titles of all these papers. So these 3 authors, they're working actively together, and the subjects are dense matter, nuclear forces, superfluidity, and different, well, condensed physics effects in dense matter, superfluidity of different types, and on different interactions taking into account different pairing times and different magnetic field effects and so on. And for today, the title of the talk is Strong Coupling Effects of Pairing Fluctuations and Anderson-Bogoliubov mode in the neutron singlet state superfluids and neutron stars. So, Inatani-san, please begin your talk.
Okay,
Thank you very much for agreeing to give this talk for us. It will be a pleasure, I'm sure.
thank you for introduction. So I'm sharing the slide. Can you see the slide?
Absolutely.
Okay. Okay, thank you for the introduction and good morning, everyone. Sorry. Yeah. So I am Daisuke Inotani of Keio University, Kanagawa in Japan. And before I start, I'd like to thank Professor Yakovlev for inviting me to talk in this seminar. So today I am here to talk to you about our current research in this paper, so in which we theoretically investigate the effect of thermal and quantum fluctuations of superfluid order parameters in singlet S0 neutron superfluid in the neutron stars. Okay, the collaborators of this work is Yasui, Professor Yasui and Professor Nita. They are also working in Keio University. Okay, this slide showed the outline of this talk. As an introduction, I will explain about, I will briefly review about the neutron superfluid in the neutron stars. And recently, singlet S0 neutron superfluid in neutron stars has attracted much attention in the viewpoint of the similarity to the BCS-BC crossover physics, which is realized in the cold atom physics. And so I will also explain about the cold atom physics and explain what is the BCS-BC crossover. And second, I will explain the formalism which I used in this work and how to make a potential to describe the neutron-neutron interaction and how to include the pairing fluctuation, fluctuation of the superfluid order parameters. And third, I will show you the numerical result for the superfluid order parameter and the chemical potential. And I will also show you that to investigate the bulk property of the neutron stars, it is very important to take into account the collective excitations. And finally, let me conclude. Let me summarize my talk. I will summarize the talk. Okay, let's start with the introduction. So neutron stars are considered as the smallest and densest object in the universe. And inside the neutron stars, the temperature is much lower than the Fermi energy of neutrons. In addition, neutron stars are under extraordinary conditions which cannot be realized in the laboratory on the Earth, so such as very rapid rotation and a very, very strong magnetic field. So in this sense, so the neutron stars are very interesting object as quantum degenerated system under extraordinary conditions. And recently, a gravitational wave from binary neutron star merger was observed. And it has been known that the more precise measurement of the gravitational wave signal make us unable to know the detail of equation of state of the nuclear matter inside the neutron stars. And to investigate the physical property of nuclear matter inside the neutron stars, the interaction between neutrons plays a crucial role. So in the next slide, we focus on the density dependence of the neutron-neutron interaction. So that right figure shows the density. Sorry. Yeah. The right figure shows the density dependence of the phase shift of nucleon-nucleon scattering in various scattering channels. So for example, this red line shows the phase shift in the singlet hetero scattering channel, and the green line shows the phase shift in the triplet P2 channel. And the positive and negative value of the phase shift means that the interaction is attractive and repulsive, respectively. And as shown this figure, in the low density region near the surface of the neutron star, singlet hetero channel attractive interaction is dominant. So because of this interaction, so neutrons form a singlet hetero pair like this figure. And this pair is spin singlet, and that total angular momentum is equal to 0. So in this low density region, singlet hetero neutron superfluid is expected to be realized. Okay. And as increasing the density, singlet hetero channel interaction gradually decreases like this, and finally turn to be repulsive. And in this region, instead of the singlet hetero interaction, the triplet P2 channel attractive interaction becomes dominant. So then, in the deeper core region, it is believed that the triplet P2 superfluid is realized as shown in this figure. The presence of the neutron superfluid inside the neutron stars is also supported by some observations. So for example, pulsar glitches and the cooling curves are well described by assuming the existence of neutron superfluid in the neutron stars. The neutron superfluidity is known to remarkably affect the thermodynamic properties. So for example, the specific heat, which is very important to investigate the cooling process of the neutron stars, and the equation of state, which is deeply related to the two solar mass problem, and so on. So in this sense, for further understanding of the neutron superfluid, it's important to know the bulk property of the neutron stars. This is our motivation to investigate the superfluidity in the neutron stars.
May I ask a question?
Yeah.
There is triplet neutron superfluidity in the core and singlet state superfluidity in the crust. So
Yes.
there is a transition from single state to triplet state pairing. And what is the uncertainty in estimating this transition density? It's around several nuclear meta densities, yeah?
Yes, so in principle we can. But so to estimate the critical density, so we have to consider both singlet hetero channel interaction and triplet P2 channel interaction simultaneously in the theory. So, but it is very difficult to calculate. And in our recent work, we consider that both interaction within the Ginzburg-Landau theory, and we have and we find that the coexistence phase of the singlet hetero superfluid and triplet P2 superfluid exists in this region, but the critical density value of the critical density. So I'm not. I did not calculate. We did not calculate.
But is it possible to say that there is some layer where both superfluidities coexist? Triplet and singlet, or no? Or there is only one superfluidity at one given element of the matter?
Sorry, I didn't catch your question.
Yeah. how can we imagine this? At high densities, superfluidity is triplet. At lower densities, it is simpler. And there is some intermediate density where there is transition from triplet to simplet.
Yes.
This, well, is there any interval of densities where both superfluidities can coexist?
Yes.
Or not? Yes.
Yes. So yeah. So at least within the Ginzburg-Landau approach, we obtain the solution of the coexistence phase.
And how wide this shell where the superfluids can coexist is?
So yeah, within our theoretical framework, there are many assumptions, of course. So yeah, so in that sense, we cannot say anything about the quantitative discussion. So we don't know the critical density or the, how to say, we did not calculate the quantitative, we did not do the quantitative calculation. Yeah, but the possibility of the coexistence phase of singlet S0 and triplet P2 superfluid was discussed.
Yeah, thank you very much. Thank you. Please continue.
Okay. Okay, so in this work, but in this talk, we focus only on the singlet S0 superfluid, this superfluid. And in this work, especially we focus on two problems of the singlet S0 neutron superfluid. And the one is how do the pairing fluctuation affect the superfluid properties? So this point has recently been discussed because of the similarity between the singlet SL neutron superfluid in the neutron stars and the BCS-BC crossover, which is realized in the cold atom physics. And I will explain it later in the next slide. And the second one is the density dependence of the singlet SL neutron-neutron interaction. And in this work, to describe the singlet SL superfluid in a wide density region of a neutron star, so we make a precise potential. Okay, in the next slide, I will explain about the ultra-cold Fermi gas, which is related to the upper problem. So cold atom is a gas of magnetically or optically trapped atoms. So this picture shows an experimental equipment of cold atom physics. And in this tiny red light, atoms are trapped. And the most powerful feature of this system is the controllability of various physical parameters. So for example, the interaction strength between atoms can be controlled by using the so-called Fishbach resonance. The density can be tuned by varying the number of atoms, and one can introduce a lattice structure by using a laser. And of course, there are fermionic atoms and bosonic atoms, so we can choose which atoms we use. So statistics of the particle, we can change the statistics of the particle. And by using this high tunability, we can design various quantum systems in this equipment. So the cold atomic gases have attracted much attention as a simulator for quantum many-body systems. And the realization of the BCS-BC crossover in ultra-cold Fermi gases is one of the most successful issues in the cold atom physics. So this right figure showed the first observation of the BCS-BC crossover. And in this figure, this figure showed the experimental result of condensation of fermionic pairs as a function of interaction strength and the temperature. And this axis showed the interaction strength, and this side is corresponding to the strong coupling side, and this side is corresponding to the weak coupling side. And this axis showed the temperature. And a finite value of
the magnetic field, I'm sorry, there is a magnetic field also. The magnetic field as well in this graph. The magnetic field.
Yes, yes. So in the cold atom physics, we use the Feshbach resonance, the so-called Feshbach resonance phenomena, to tune the interaction strengths. But so yeah, so I will not explain about the detail, but so in the cold atom physics, by varying the external magnetic field, we can tune the interaction strengths.
Yeah, thank you. Thank you. Okay.
Yeah. Yeah. And okay, finite value of the condensation means that the system is in the superfluid phase. So the border between this blue region and this light blue region corresponding to the superfluid order parameter, superfluid transition temperature. And as shown from this figure, as including the interaction strength like this, so superfluid transition temperature Tc gradually increase like this, and eventually reach some value. And this is a very typical behavior of the superfluid transition temperature in the BCS-BC crossover. Okay, in the next slide, I will explain the BCS-BC crossover in more detail. This figure shows the phase diagram of interacting Fermi gas. And this red line shows the superfluid transition temperature calculated from a strong coupling theory, including fluctuation. So, and this theory is known to well describe the BCS-BC crossover physics. And this blue line shows the superfluid temperature calculated within the mean field BCS theory for comparison. So the difference between these two lines describe the effect of the pairing fluctuation effect, okay? And in cold atom physics, KFS inverse here is conventionally used to measure the interaction strength. And here, so AS is the S-wave scattering length, and KF is the Fermi momentum. And when KFS inverse has negative large value, like in this region, the interaction is very weak. Now, on the other hand, KFS inverse has positive large value, like in this regime, the interaction is very strong. Okay. So in the BCS-BC crossover phenomena with increasing the interaction strength, the Fermi superfluid, well described by the mean field theory in the BCS, in the weak coupling regime, continuously changes to the Bose-Einstein condensation of the tightly binding molecular boson in the strong coupling regime. Okay, we start with in the strong coupling regime. In the weak coupling regime. In the weak coupling regime, the Fermi superfluid is well described by the mean field BCS theory. And in this region, in the normal phase above Tc, there are no Cooper pairs. So both pairing and superfluid phase transition simultaneously occur at the same temperature. With increasing the interaction strength, the superfluid transition temperature suppressed by the fluctuation as shown in this figure. So the difference between these two Tc become very large. That means the fluctuation effect is very important. And in the in this intermediate regime, which is referred as the crossover regime, it is known that the fluctuating pair are formed even above Tc. So in this region, the pairing fluctuations remarkably affect the various physical properties. For example, density of states and spin susceptibility, equation of state, and specific heat, and so on. And in the strong coupling regime, the Fermi atoms form tightly binding molecular bosons, and the system can be described as the free Bose gas. And in this region, the superfluidity is understood as the Bose-Einstein condensation of the molecular boson, tightly binding molecular boson. So in this slide, I would like to emphasize that the pairing fluctuation is very important in the crossover regime or the intermediate coupling regime. Okay. So in the next slide, we compare the BCS-BC crossover with the singlet S0 neutron superfluid. So in the cold atom case, the scattering length can be tuned experimentally, so by varying the external magnetic field. On the other hand, in the neutron star, scattering length AS is equal to negative 18.8 femtometers. And this value is fixed, of course, in the neutron stars. However, the Fermi momentum, KF, or density of neutrons becomes large as one goes deeper into the star. Okay. As a result, the parameter KF's inverse approaches zero as increasing the density. And when we use the typical value of KF in neutron stars, so for example, 1 femtometer inverse or 2 femtometer inverse, so we obtain the KFS inverse is equals to negative 0.1. So this value is corresponding to the crossover regime, which is shown in the previous slide. So in this regime, the pairing fluctuation is very important. So in this sense, the singlet S0 neutron superfluid is similar to the fermiatomic superfluid in the weak coupling and the crossover regime. Thus, to understand singlet S0 superfluid in the neutron stars, the pairing fluctuations should be taken into account.
Okay, and what about the densities? This Fermi momentum equal to 2 inverse Fermis. Well, it corresponds to which densities in the star compared with nuclear matter density?
Okay. Saturation density is corresponding to KF is equals to 1.7 something.
So it is around saturation, yeah?
So yeah, it's near the saturation density, 2 femtometer.
I see. Thank you.
Okay, next I will explain the other problem about the density dependence of the neutron-neutron interaction. And this figure shows the density dependence of the phase shift in the S-wave scattering channel. And this blue dot line shows the experimental result. So the phase shift is estimated from the nucleon-nucleon scattering experiment. Okay, to reproduce the density dependence of this phase shift, so in this, this phase shift, the effective range expansion has been widely used. In this approximation, one expands the cotangent of the phase shift in the momentum, like this expression. And we use the AS and the scattering length and effective range as fitting parameters. And this red line shows the phase shift obtained within the effective range expansion. So in the low momentum region, so corresponding to the low density region, so yeah, effective range expansion will describe the experimental phase shift in the singlet S0 channel. However, in the higher density region, the phase shift obtained within the effective range expansion deviates from the experimental value. So in this high density region, so effective range expansion is no longer a good approximation. So for understanding the singlet tensor superfluidity in the higher density region, so one needs a more precise potential than the effective range expansion. Okay, let me summarize the motivation of this work. So in this work, we consider the two problems. One problem is the pairing fluctuation. The other problem is the density dependence of the superfluid, the singlet tensor neutron-neutron interaction. And for the pairing fluctuation, we include the pairing fluctuation by using the Nogel and Schmidt-Link scheme, NSR scheme, so which is known to well describe the BCS-BC crossover physics in the cold atom physics. And for the potential, we make a precise potential describing the singlet tensor phase shift in the wide region of density region. A wide range of the density region in neutron stars. By using these two methods, we investigate the strong coupling effect in neutron singlet tensor superfluid, covering a wider range of the density and temperature from 0 to superfluid transition temperature Tc. And this kind of work have been done by some authors. For example, in this work, so they investigate the thermodynamic property in the superfluid phase, but they use the effective range expansion. So this work cannot be accessed. This method cannot be used for the higher density region. So in this work, they use the precise potential, which can describe the phase shift in the high density region, but they investigate only the property in the physical properties in the normal phase. So the different point from the different point of our work from this previous work as the by using a precise potential, and we investigate the strong coupling effect in the superfluid phase. This is a different point, okay?
Mm-hmm.
Sorry. Okay, next. Next, I will explain about the formalism which I use in this work. So we start from the Hamiltonian describing the neutrons with singlet S0 attractive interaction. So which is given by this expression. And the first term describes the kinetic energy measured from the chemical potential, mu. Yeah. The kinetic energy is given by this expression. And the second term describes the singlet S0 attractive interaction between neutrons. And for the interaction, so we assume it to be a separable potential, which is written by this expression with the coupling constant US and form factor Fc. Form factor is the function of the momentum. And in our work, the coupling constant and the form factor are determined to reproduce the value of the singlet S0 phase shift estimated from the result of nucleon-nucleon scattering experiments.
Yeah, but
okay.
In principle, sorry, may I ask, but in principle, these values in the these ingredients of the potential, they can be influenced by many body effects, yeah?
Mm-hmm. Sorry?
These parameters of the potential, they can be, well, not for the free neutrons. They can be, in principle, you can complicate your picture and introduce, well, more complicated functions.
Yes.
Yeah. Thank
Yeah,
you.
so we don't know the specific form or the form factor, but in this work, we numerically determine the form factor and the coupling constant.
Yeah.
Okay, I will explain it in this slide. Okay.
Good.
So the relation between the interaction and the phase shift can be obtained by solving the two-body scattering problem. And the equation is given by this expression. Okay, and pi is the pair correlation function and diagrammatically given by this figure. And by numerically solving this equation for a given phase shift, so we can determine the US coupling constant and form factor.
Mm-hmm.
Okay. And this upper figure shows the calculated form factor and without any assumption. Okay. And the lower figure shows the phase shift calculated from our potential by this red line. Okay. And as shown from this figure, our potential well reproduces the experimental value is shown by this green line. Okay. And as shown from this figure, our potential will reproduce the experimental value of the phase shift in this momentum region. Okay. But here we note that our potential can reproduce only positive value of the phase shift. In other words, our potential can describe only attractive part of the interaction. So we take F's form factor is vanished in the momentum region where the phase shift is negative for simplicity in this work. So this means that we ignore the repulsive part of the singlet ester interaction. Okay. And in this figure, we show the phase shift obtained within the effective range expansion. This line, this blue line, and compared to the effective range expansion, we find that our potential can be used for a far higher density region than the effective range expansion. Okay, this is the potential which I use. And next, I will explain how to include the superfluid fluctuations. And in this work, we use the NSR scheme. NSR scheme is known to well describe the BCS-BC crossover phenomena. And first, by introducing the, for this purpose, by introducing the superfluid order parameter by using this expression, and using the number representation with number operators, and we divide the Hamiltonian into two parts as shown in this expression. And the first term describes the mean field contribution, mean field term, and the second term describes the fluctuation part from the mean field value. And here, rho is the generalized density operator, which is defined by this expression, with the Pauli matrix acting on the Nabokov space. And rho 1 term physically means the amplitude fluctuation, and rho 2 term physically means the phase fluctuation of the superfluid order parameter, respectively. Okay. And in the NSR scheme, this fluctuation part is taken into account as the strong coupling correction of the thermodynamic potential, like this expression. And as a result, the thermodynamic potential is given by the sum of the mean field part and the contribution from the pairing fluctuation. The mean field part is given by this expression, and on the other hand, the fluctuation part of the thermodynamic potential is diagrammatically given by these diagrams. And in these diagrams, this solid line describes the so-called 2x2 Goff-Green's function within the mean field level, G0, this one. And the dotted line shows describe the singlet S0 interaction. Okay, by using this thermodynamic potential, through the thermodynamic relation and the saddle point condition, so we obtain the particle number equation and gap equation. And by solving self-consistently these equations, we obtain the chemical potential and the delta. So yeah, I will explain the detail of the calculation. So by solving the particle number equation for given n and the delta, so we first determine the chemical potential mu. So this is the first step of our calculation. And in the next step, we check whether this chemical potential, calculated chemical potential, and the n and delta satisfy the gap equation. And if not, we change the value of the delta and return to step 1. And repeating this procedure, finally we obtain the self-consistent solution of chemical potential mu and superfluid order parameter delta for given n. Okay. Sorry. So here we comment that the gap equation has the same form as one within the mean field theory. So, and the strong coupling effect are considered in the gap equation only through the value of the chemical potential. And this is because we derive the gap equation from the saddle point condition for the mean field part of the thermodynamic potential, omega mean field. So in this regard, the NSR scheme is not completely self-consistent theoretical work. However, this gap equation is very important because this gap equation guarantees the existence of the gapless collective excitations associated with the phase fluctuation of delta. And it is known that the existence of these gapless collective excitations is very important for properly considering the fluctuation effects. So we use this saddle point condition to derive the gap equation. Okay, in the next slide, I will explain the physical meaning of this fluctuation, the pairing fluctuation contribution to the particle number. So as shown in the previous slide, within the NSR scheme, so the particle number is given by the sum of the mean field part and the fluctuation part. And the fluctuation are considered only as the correction of the correction to the particle number. So in this equation, the mean field contribution to the particle number physically means the number of unpaired neutron and the number of the condensed Cooper pairs, and which is given by this expression. And on the other hand, the fluctuation contribution delta n means the number of the non-condensed Cooper pair below in the superfluid phase below Tc, and the preformed Cooper pair in the normal phase above Tc. This is the physical meaning of the delta n. And in this, so here I showed.
So may I ask, so does it mean that above Tc you will have also the effect of Cooper pairing?
Mm-hmm.
Yes?
Yes.
Arigato.
Yeah.
Okay, thank you.
Okay, in this expression, so gamma is given by these diagrams, Feynman diagrams, and the gamma physically describe the propagator of the non-condensed pair. So in other words, gamma describe the bosonic collective excitations associated with the phase and amplitude fluctuations of the superfluid order parameter. So this is the meaning of the fluctuation in the NSR scheme.
Sorry, can I ask, how do you derive Tc in this scheme?
Okay. So, yeah, the equation for Tc can be obtained by setting the delta equals to 0 in this gap equation. And by solving these two equations for T, so we obtain the superfluid order parameter, superfluid transition temperature.
Okay, but delta delta is order parameter here. Okay. So
It's included.
So this is, but this is not the energy of the condensate, right? Or not the condensate of the dissociation of the pi pair.
Yeah. So, but so how do you mean by the condensation?
No. I mean, I was misspelled. I mean the energy of the dissociation of the pair. So you have the pairs above Tc, which have the dissociation energy. And how does this related to the parameter? So this does this energy relates to this delta?
Sorry, I didn't get your question.
Well, then when the pair formed, then the pair is formed. There is some binding energy or dissociation energy of this pair. So how this energy relates to the order parameter, to the delta?
So above Tc, the binding energy of the preformed Cooper pair is not related to the superfluid order parameter, of course, because in the normal phase, superfluid order parameter is 0. Okay. And
right.
So yeah, in principle, we can estimate the binding energy of the preformed Cooper pair, but it's very complicated. And in this work, we focus on the superfluid phase. So I will not explain the detail, but in principle, we can estimate the binding energy of the preformed Cooper pair.
Thank you.
Yeah. And the delta is related to the condensation energy of the superfluidity, even in this formalism. Okay.
Thanks.
Okay.
Excuse me.
Yeah.
May I ask you a question?
Yes, of course.
Yeah. What is the difference between condensed Cooper pairs and non-condensed Cooper pairs below Tc?
Okay. So condensed Cooper pair means so in the superfluid phase, the neutrons form a pair, and they as decreasing the temperature, so they are condensed at the zero energy state. Then the BEC become large. Okay, so so condensed pair is mean the boson pairs with zero energy, and the non-condensed Cooper pair means the excited by the excited Cooper pairs by fluctuations.
Oh, okay.
Okay. What does it mean excited? Excited Cooper pairs. Do they have a non-zero momentum or something like that?
Yes, non-zero. Yeah, they have a non-zero momentum and non-zero energy. So in the results section, I will show you the dispersion relation of this non-condensed Cooper pairs. So for example, in the Bose gas, so there are sound mode as a collective excitation and a finite temperature region. So not all the bosons condensed, and some bosons are thermally excited in their collective excitation. So this non-condensed Cooper pair is same as the thermally excited boson in the Bose gas.
Okay, thank you.
Okay. Okay, let's move on to the result. So this figure shows the calculated superfluid order parameter as a function of the temperature and the density of neutrons. And this blue line shows the superfluid transition temperature, Tc. And starting from low density region, Tc first increases as increasing that density. And Tc has maximum value around Kf equals 1 femtometer inverse. Then Tc turns to decrease, and finally vanishes at the critical density. And this non-monotonic behavior is because of the density dependence of the form factor. So remembering that the form factor is a decreasing function of the momentum or the density, as increasing the density, the interaction strength at the film surface is suppressed. And in the very high momentum region, the form factor vanishes in our model, and the superfluid is also broken in that regime. And the vanishing Tc means that the quantum phase transition from the superfluid phase to the normal fluid phase occur at the t equals 0. And in this slide, we would like to emphasize that this quantum phase transition at t equals 0 cannot be described by the effective range expansion. Because within this approximation, the attractive interaction cannot vanish even at the high density limit. So this quantum phase transition is new result within our precise potential. Okay, in the next slide, we focus on the result at the t equals 0. Okay. So this figure shows the superfluid order parameter and the chemical potential. In each figure, we also show that the density dependence of the superfluid order parameter and the chemical potential are calculated within the mean field theory by green line. Okay, and the difference between these lines is corresponding to the effect of the fluctuation. Okay, first, as we focus on the chemical potential, as shown in this right figure, the chemical potential is always suppressed by the pairing fluctuations. But on the other hand, the superfluid order parameter is suppressed in the low density region, while it is enhanced in the high density region due to the pairing fluctuation. And this opposite trend of the effect of the pairing fluctuation on the superfluid order parameter between the low density regime and the high density regime can be understood as follows. So first we focus on the low density region. And in the NSL scheme, the particle number is given as the sum of the mean field contribution and the fluctuation contribution. And the mean field contribution corresponding to the fermionic component, and the fluctuation contribution is corresponding to the non-condensed pair. Okay. Thus, within the NSL scheme, due to the finite value of the delta n, so n mean field is reduced compared to the mean field theory. Okay. So as a result, the Fermi surface, Fermi sphere of Newton, Fermi sphere of this fermionic component is shrink. So this can be seen from the suppression of the chemical potential. Then, because the pairing is supported by the Fermi surface effect in the superfluidity, the superfluid order parameter becomes smaller due to the fluctuation. And this behavior, this suppression is consistent with the ordinary BCS-BC crossover phenomena in coordinate physics. However, in the higher density region, the situation changes. So the suppression of the chemical potential leads not only shrinking the Fermi surface, but also enhancement of the interaction at the Fermi surface. Okay, noting that the form factor is a decreased function, as shown in this figure, of the momentum, and the effective Fermi momentum is given by square root of 2 times m times mu. Okay, and the interaction strength at the Fermi surface in the NSL scheme is so stronger than one in the mean field theory, because this effective Fermi surface, this effective Fermi momentum is smaller than the one within the mean field theory. Okay, in the higher density region, so this effect becomes more remarkable than the suppression of pairing by shrinking the film surface. As a result, in this region, delta is enhanced by the fluctuation. So this is because the opposite trend of the pairing fluctuations to on the superfluid order parameters. Okay, in the next slide, we will see the physical property of the superfluid fluctuations. So as we've seen, the fluctuation contribution to the particle number is given by these expressions. And the gamma in this expression describes the propagation of the collective excitations associated with the fluctuations of the superfluid order parameter. And by from the analytic continuation of gamma, so one can obtain the spectral function of the collective excitation as shown in this figure. And from this figure, we find the sharp peak structure along linear dispersion relation like this. And this peak is corresponding to the collective excitation associated with the phase fluctuation, which is known as the Anderson-Bogoliubov mode. And this figure schematically shows the free energy as a function of superfluid order parameter. And the Anderson-Bogoliubov mode is corresponding to the oscillation in this direction. Okay. And the other collective excitation are associated with the amplitude fluctuation, so in this direction. So they are known as the Higgs mode. However, this Higgs mode is gapped mode. So in the low temperature region, so this Higgs mode cannot appear, does not appear in the spectral function. So our result indicates that the non-condensed Cooper pair is dominated by the gapless Anderson-Bogoliubov mode. Okay. And the single particle excitation have energy gap due to the superfluid order parameter delta. So these excitations are strongly suppressed as decreasing the temperature. So as a result, in the low temperature regime, the thermodynamic properties are dominated by the gapless Anderson-Bogoliubov mode. So for understanding the thermodynamic property of the neutron stars, it is very important to consider this gapless Anderson-Bogoliubov mode. Okay. And in this slide, we will see how much neutrons are counted as a fluctuation part. This figure shows the density dependence of the mean field and mean field part and the fluctuation part contribution to the particle number. The left figure and the right figure show the result at t equals 0 and t equals Tc respectively. And the red line shows the contribution from the fluctuation, and the green line shows the mean field contribution. And as shown from these figures, delta n rapidly increases as increasing the density, and it accounts for about 40% of total neutrons. So this result indicates that the fluctuation might qualitatively affect the physical properties of singlet S0 neutron superfluid. Okay, next let me talk to you about our future works. So in the present work, we find the thermodynamic properties and are dominated by the gapless Anderson-Bogoliubov mode. And in the context of the singlet S0 neutron superfluid, so this point has been first indicated in this paper. Okay? And the authors discussed how the existence of the gapless collective excitation changed the low temperature behavior of the thermodynamic properties. So for example, without considering the collective excitations, the specific heat exponentially decreases in the low temperature regime, like this. So due to the gap structure of the single particle excitation. However, when we consider the gapless excitation, the temperature dependence qualitatively changes. So in this case, the specific heat is proportional to T to the third power. So but in this previous work, they used the random phase approximation in which the value of the superfluid order parameter and the chemical potential are estimated within the mean field theory. So by using our NSR scheme, so one can more quantitatively calculate the various thermodynamic quantities in a wide density region and temperature region. This is one of our future works. And second, we are interested in the superfluid and further higher density region. So to investigate the superfluid in this region, so we should consider not only singlet S0 interaction, but also triplet P2 attractive interaction. And we should also include the repulsive part of the singlet S0 interaction, which is ignored in the present work. And in addition, it has been reported our NSR scheme might overestimate the fluctuations in the high density region in the normal phase, in this paper. So it is necessary to modify our NSR scheme to access the high density region. This point was discussed in our paper and in this reference. Okay, for the triplet P2 superfluid, we recently discussed the possibility. Of the singlet S0 and triplet P2 superfluidity by analyzing the Ginzburg-Landau free energy in this paper. And as a result, triplet P2 superfluid can coexist with the singlet S0 superfluid in the presence of the magnetic field. And when the interaction strengths of the singlet S0 channel and the triplet P2 channel are comparable.
Sorry, may I ask here a question?
Yeah.
So what do you mean by the coexistence of these two superfluids? So you have the two types of Kuiper pairs, right? With so two types of molecules with different momenta, and then they both condense. But what about the phase? So one condensation already broke the symmetry. So the second one shouldn't add another broken symmetry or not? Or am I wrong? So what is exactly what do you mean by the coexistence of the two superfluids?
Okay. Maybe relative phase between the singlet S0 superfluid and the order parameter and the triplet P2 superfluid order parameter is fixed. So in that sense, only one symmetry. How to say? So, but in this phase, so the both singlet S0 superfluid order parameter and the triplet P2 superfluid order parameter have finite value. In this sense, the coexistence of singlet S0 and triplet P2 superfluid occur in this region. But maybe I'm not sure. Sorry, but I guess the relative phase between these two superfluid is fixed. I guess.
I see. Thank you.
Okay.
And may I ask, what are the parameters for which these figures are drawn? This is what is the density, and there is a magnetic field here, yeah?
In this work?
What is these figures, they present the results of calculations, yeah?
Sorry?
For which density?
Okay.
Yeah.
So, in this work, we assume that the superfluid transition temperature of singlet S0 superfluid and the superfluid transition temperature of triplet P2 superfluid are same. this is the condition for the calculation.
Mhm.
And we, how to say, but we do not use the specific value of the density or something.
I see. Right.
Yeah.
Mhm.
What is B in the yes, in the vertical scale?
This
B.
this one is the magnetic field.
Magnetic.
Yeah, external magnetic field.
Thank you.
Yeah. So yeah, if
Excuse me, may I ask you? Excuse me, I'm sorry. Can
It's
you
okay.
go to the previous slide, please?
previous slide, this one.
Yeah.
Yeah.
In neutron stars, you also have electrons, which will also contribute to specific heat.
Yes.
So I was wondering whether this contribution due to Anderson mode will be bigger or smaller than the electron contribution.
Yeah, I'm not sure. I have no idea about the contribution from the electrons to the specific heat, but yeah, at least
it is proportional to temperature.
Proportional to
T squared.
It's a standard Fermi gas contribution proportional to temperature to the first T to 1.
Okay, but the number of the electrons and the neutron is different, right?
That's right.
Yeah, so in that sense, so I cannot qualitatively estimate the ratio of the between of the electrons and contribution from the electrons and neutrons. And so in the sense, I'm not sure. I have no idea about that. Okay.
Okay, thanks.
So at least the temperature dependence is changes by considering the Anderson-Boch mode. Okay. Okay, if you are interested in this topic about the coexistence of singlet S0 and triplet beta superfluid, so yeah, please refer this paper. Okay. Okay, let me summarize my talk. So we have discussed the effect of the superfluid fluctuations in singlet S0 superfluid in the neutron stars. And to describe the neutron-neutron interaction, so we have constructed a separable potential to reproduce the singlet S0 phase shift. And include the superfluid fluctuations within the NSL theory, so we have self-consistently determined the superfluid order parameter and the chemical potential. And we have shown that the superfluid fluctuations are dominated by the gapless Anderson-Boch mode. And our results indicate that for studying the thermodynamic quantities, such as the equation of states, specific heat, and compressibility in the neutron stars, so the superfluid fluctuation should be taken into account and important. Okay, thank you for your attention.
Thank you very much. Thank you very much. Well, perhaps some questions. I have a question. May I ask a question?
Yes.
Yeah. So what about denser regions of neutron stars? If you have densities higher than the nuclear matter density, then there will be triplet state pairing. What is your opinion? Will that triplet state pairing strongly affect the chemical potential of neutrons?
It's a difficult question, but
okay, so I understood.
Yeah, so yeah, for example, so by when we estimate something, so maybe we use the value of the specific heat or something. sorry, how to say? Yeah, it's very difficult question.
Okay, thank you very much.
Yeah, sorry.
More questions?
Can I ask you? Yes, the next slide. Can you show me the next slide, please?
Next slide.
No. The slide number 29. Yeah, 29.
29.
Almost the last one. Yes,
Okay.
the last one. So this figure showing the dependence of chemical potential on the wave number of the neutron wave number. It says
This
to
one?
us that yes,
Yep.
it says to us that it's that superfluidity strongly affects calculation the chemical potential of neutrons. So it's a better approximation to use to take the chemical potentials from the Landau theory when calculating, if you know the number density of neutrons.
Okay. What is that Landau theory? I'm not.
Well,
I don't know.
Fermi liquid theory.
Okay, Fermi liquid theory. Okay.
Without completely neglecting superfluidity effects.
Yes.
So it's a better approximation. In the
Maybe
crust,
that. In the singlet tensor superfluid phase, so NSR scheme is better, I think, to calculate the chemical potential.
But I see here a difference about 40% in the crust in chemical potential. If we can compare the your calculation with the BCS calculation.
Okay. So sorry. Do you mean by this?
Because to calculate chemical potential within the BCS scheme, if I understand correctly, we do not need to know the BCS, the details of BCS.
Just.
Is it correct? Is it a correct statement that this green dashed line, to calculate this green dashed line, we do not actually need anything about the superfluidity?
So do you mean by how to say, the chemical potential is very different from the calculated one calculated within the Fermi liquid theory? No.
I know that if we are within the BCS scheme, neutron chemical potential can be calculated completely neglecting the superfluid effects within the BCS scheme. Do you agree?
Yes.
So this green dashed line can be calculated completely neglecting superfluid effects.
Superfluid effect means the superfluid fluctuation effect? No.
No, this green line is obtained neglecting superfluid fluctuations. If I understand correctly.
Maybe no. So because
I'm talking about the green line.
Yes. I understand.
Yeah.
So yeah. So when we calculate this green line, so we solve the particle number equation without the fluctuation.
Yeah.
Okay. And in this equation, the superfluid order parameter is included in the EK in this part. And so in that sense, the superfluidity affect the value of the chemical potential.
But this effect of superfluidity is of the order of gap squared divided by Fermi energy.
Yes.
So it's small.
Maybe it's small. Yeah. So yeah, in a sense, the chemical potential can be roughly estimated by using the normal fluid theory.
It's a good approximation, at least if we are talking about BCS scheme. It's a good approximation. If we postulate that BCS is correct, then it's a good approximation for sure to calculate chemical potential from the from the non-superfluid matter, completely neglecting superfluidity. And you say that the red line, the account for fluctuations, dramatically affects the chemical potential.
Yes, yes.
Does it mean that the fluctuation Hamiltonian is in fact comparable to the contribution of normal Hamiltonian?
Yes.
And how do these results correspond to other calculations available in the literature? Because there are plenty of calculations of gaps and also thermodynamic properties, which I suspect already taken into account the fluctuations. So how do your results correspond to those available in the literature?
Sorry?
How do your results correspond to those available in the literature?
What kind of literature?
There are calculations of the superfluid gaps in the neutron star crust in the literature, and many of them take into account the many body effects.
Okay.
So I wonder how your results correspond to those in the literature.
So,
because for me it's quite unusual. Your finding that chemical potential is affected to very much by the superfluidity is quite unusual, I would say.
Okay, so in our calculation, so delta n, so number of the non-condensed Cooper pair is taken into account in the particle number. Okay, and this value reaches 40% of the total number of the neutrons. Okay.
Yeah, that's the question.
Yeah, that's what surprises me, in fact.
Okay. Okay. Yeah.
Ksenia, would you like to ask questions?
Yes.
No. I'm addressing Ksenia Levinfish. Wow. Personally, I cannot hear.
Yes, sorry, I cannot hear you.
Okay.
Can you hear me?
Can you speak louder?
I try. Natanya-san, would you comment about compressibility, Newton's star method?
I'm sorry, I cannot get you.
I think she's asking about the compressibility of neutron star matter, but it's very faint sound. Maybe Ksenia can write in chat.
Okay.
Could you ask him about the range of change of compressibility in density? This affects only a small range in density. The change in compressibility of neutron star matter, is it right?
Compressibility?
I could.
Sorry, I cannot catch your question.
Of course, compressibility will be affected if the chemical potential so dramatically changes.
In what density interval?
Sorry?
Well, we do not know for sure, because in which gap intervals but I don't know.
Sorry, thank you.
Okay. Ksenia, can you write down in chat? In chat.
May I also ask an additional question?
Sure.
This your final result, gap versus wave number, Newton wave number. I see that this red line at large densities, we have something like, well,
this one?
No. Can you return to the slide number 29?
Okay.
So I mean gap versus wave number. Yes, this one.
Okay, this one. Okay.
So the cross-core interface occurs something at 1.3 inverse Fermi.
Here.
So at such a density, we have delta of the order of 2 MeV. And so does it mean that in the outer core, we in fact will have a singlet state pairing rather than triplet one?
Yeah, so yeah, in this work, we do not consider the triplet P2 interaction. So yeah, I'm not sure when we considered both interactions, so maybe this order parameter changes, but so at least when we consider only the singlet tensor superfluid, singlet tensor interaction, so the order parameter is given by this value. Okay.
Okay.
And yeah. Hi.
May I ask a question?
Sure.
Are your results applicable to proton singlet superfluidity?
Proton.
Yeah.
Yeah, maybe in principle, yeah, yes, but so I guess the Coulomb interaction between proton is very difficult to create within this formalism, because in this formalism, so we consider the fluctuation in the superfluid pairing channel only in the pairing channel, but the Coulomb interaction as a repulsive interaction and the density fluctuation become dominant.
So you think that Coulomb interaction of protons is important in this problem? Yeah, it sounds strange for me because a nuclear interaction between strong interaction between protons is much stronger than Coulomb interaction. It seems that this problem completely driven by strong proton interaction.
Okay. So yeah, if we can neglect, we can ignore the Coulomb interaction between protons. Yeah, this method can be extended to the proton case.
Okay, thank you.
So in the chat, I have a question. So I get the question. Could you please comment on how strong the compressibility will be affected by the fluctuation in which density range? Okay. Actually, the how to say? So compressibility below the superfluid transition temperature. How to say? So okay, in the BCS-BC crossover physics, in the cold atom physics, cold atom gases, so the strong coupling effect on compressibility have been discussed. But in the superfluid phase, to calculate the compressibility, including the pairing fluctuation, is very, very difficult. Because so when we consider the free Bose gas, in the in the superfluid phase, the compressibility diverges because the So to stop this divergence of the compressibility, we have to include the repulsive interaction between the bosons. Okay. So, but in our NSR scheme, so the compressibility is considered, also the fluctuation is considered as the free bosonic propagation. So in that sense, the let's say repulsive interaction between pair have to consider to calculate the compressibility below TC. Okay, so it is very difficult question, difficult calculation to calculate the compressibility, including the superfluid fluctuations. Yeah, in the superfluid phase.
Thank you.
Okay. Okay.
Okay, no questions. No comments. Wow. Okay. Well, very well.
Okay, may I, well, try to return to the question of Misha and try to reformulate it. So you found this 40% of non-condensed Kuiper pairs. So is there in the literature something similar? Some similar findings somewhere in the literature, do you know? Related to neutron stars?
So can I?
So you found that, well, in some cases, about 40% of the Kuiper pairs are non-condensed, right?
Yes.
So, right. So are there any similar calculations in the literature? Had anybody obtained something similar or something close to these numbers or not?
So in the BCS-BC crossover phenomena in the cold atom physics, so 40% non-condensed Kuiper pairs are not so large.
Right. I mean, in literature related to neutron stars.
Yeah. So and the neutron stars corresponding to the crossover regime. So yeah, as shown in the introduction. Yeah, here. Crossover regime. So in this regime, the non-condensed Kuiper pair become 40%. This fact is not so strange.
Right, I agree, but the question is not well physical, but historical, so to say. So, did anybody include considered these in the context of neutron stars? Because there are many gap calculations, or you are the first one who included these effects of these crossover effects in context of neutron star pairing. So nobody in the context of the gaps of the gap calculations in the neutron stars, nobody yet have considered these crossover region properly, right?
Okay. So yeah.
No, I mean it's a question. Are you the first one, or there were already some calculations of
Okay.
say gaps, which included these effects.
Okay, so I understand that. So, for example, in this work, so pairing fluctuation are taken into account and they investigate the thermodynamic property in the superfluid phase, and by using the potential within the effective range expansion. So in this work, the fluctuation discussed in this work.
And do they also obtain like 40%? 40%?
Yeah, in this paper, they did not explicitly show the particle number fluctuation contribution to the particle number, but yeah, because so I am the co-author, so yeah, maybe in their work, in this work, same magnitude of the delta n is obtained. Yeah.
But the parameters were quite different, I believe, and that work, well, it was devoted to other physical systems, not to neutron stars.
Sorry, I didn't get your question.
Okay, this paper by Vic, Tayama, Anisha, and so on, published in Physical Review A, it was not devoted to neutron stars. It was not calculated for the parameters typical for neutron stars. I do not know this paper. I have not read it.
This one?
Yeah.
Okay. So yeah, in this paper, oh, sorry. I'm not sure about the. I guess in this, sorry. In this paper, they calculate the internal energy and the superfluid order parameter as a function of the the density at t equals 0.
Okay.
Okay.
Okay. Well, Michael, what do you think? Misha, what do you think? Will we continue this discussion, or perhaps we will just?
No. I have sent some reference in the chat. So you can look at this. It's figure 10 in this, for example, in this review article, and you can look at the references which calculate the single state gaps for neutrons in the crust, taking into account many body effects. I'm sure fluctuations are already taken into account in these very complicated calculations. So look at it, and maybe you will find something useful in this reference.
So, well, the main question why it is, the difference of the chemical potential is so large here.
Yes, because it changed everything,
Yeah.
all of the neutron star crust.
This is, the bottom of the crust, I would say.
Not really the bottom. It's a substantial part of the inner crust will be affected.
Yeah. Okay, but Misha, we will not read this paper just now.
Yes, it's just for information for information. For the future.
Thank you very much for this information. Then more questions. If I'm asking if there are more questions to the speaker. If not, then I think that it was a very useful seminar for us, and I think that we will think it over and perhaps contact speaker again if we have some questions. It's very good that the seminar excited so many questions among people who are attending. Well, thank you very much.
Thank you very much.
It was wonderful. So the seminar is over, and the next seminar, it will be the next week. It will be the talk by Nesterenek about cosmic masers. So goodbye, sayonara.
Hi, sayonara.